Good morning, ladies and gentlemen. Shall we begin? Wait, you guys have seen that word before, yes? In day-to-day when we talk about how much do you weigh? What weight are you? You can throw those words around like it's nothing, right? We step on the scale, we get a number. But in physics, in science, we need definitions to go with those words. And so when we talk about weight in physics, weight is the force of gravity. Weight is the force of gravity acting on an object. And we know that the mass of an object times the gravity gives us the force of gravity. How much does a 1 kilogram mass weigh?
Whoa.
Let's throw it on here real quick. What does it say?
Well, it's right around 10, isn't it?
Okay.
And now it's less than 10.
So we have a 1 kilogram mass. The acceleration due to gravity is 10 meters per second squared. And we get 10 newtons, right? And that's what we just saw. So it's hanging there, 1 kilogram. You know, it's true. And what's the importance of this?
Well, you can use it for all kinds of things.
Yeah, this is Newton's second law. We can use it.
I thought weight was pounds.
Ooh.
Sorry.
That's a good definition for the non-physics classroom. Okay, here we go. Can you touch something without touching it?
Can you touch something without it touching you? That's a silly question. It touched you.
Okay, so think about it. Here we've got 2 comets. And it looks like they've been joined together somehow with this little centerpiece right here. Well, side note, it took us 10 years to get there.
Wow.
Crazy, right? But the question here is, how did this happen? How did these 2 separate comets come together and form between this little small bridge thing in the middle here?
Are you sure that's not KFC?
chicken wing, chicken leg. So it was the Rosetta spacecraft, landing site, and all of that. But what happens was, the theory is that gravity pulled these 2 comets together. And so we got this formation,
yeah.
Right? And it's really cool because if you think about this spacecraft, we had to literally do, not we, whoever did it, rocket science. Like, you hear that term being thrown around, like, that's rocket science. Well, this is really rocket science.
That's your rocket science right
Yeah,
there.
I mean, you have to, figure out what the correct speed is, the trajectory, just so it can hit this thing in time, millions of billions of miles away. It's very, very cool, right? But the moral of the story here is we want to talk about Newton's third law. Forces come in pairs. I want to emphasize something real quick for you guys that I forgot to mention before. When we talk about how forces come in pairs, it doesn't happen one and then the other, right? They're happening at the same time, simultaneously. So when we say that forces come in pairs, it's important to note that it's simultaneous. When 2 objects interact, one exerts a force on the other. Does that mean that I'm exerting a force on you right now? And you
Gravity!
Yeah. There is a simultaneous force exerted back, equal in magnitude and opposite in direction. Think back to those comets, right? So one Comet A, was exerting a force on Comet B, while Comet B was exerting a force on Comet A, and then that force, gravity, pulled them together.
Cool.
Yeah, okay. Where was Newton's third law at work when you push the bubble cart? The bubble cart!
Bubble cart!
Bubble cart! Okay, all right. So,
You're touching it, it's touching you.
okay, so I'm touching the cart, it's touching me. That's the first one. What about the cart on the table? And then the table back on the cart, right?
Yep.
That's the second one. What else do we have?
How come it's not floating off the table?
Oh, so we have the cart exerting a force on the ground, Earth, gravity.
Oh, yeah.
Force of gravity. So we've got these 3 things. You and the bubble cart and you. Table and cart and table. And then cart and ground and cart.
The Earth.
The Earth, right? Okay. Newton's first law. That was inertia. How can you remember this? Ho ho ho! First law, the letter I looks like a 1.
Done.
Easy
We can do
peasy.
this.
Easy.
We can do this.
An object in motion at constant velocity in a straight line path will remain in motion unless acted on by an outside force.
I've heard that before. That's Newton's first law.
Yeah. An object at rest will remain at rest unless acted on by an outside force.
Okay.
Okay. Newton, tree apple. Newton asked, why doesn't the moon follow a straight line path through space?
Why doesn't it do that?
Yeah, because shouldn't it be going in a straight line?
That's his first law.
Yeah, okay. Well, Newton said, because apparently Newton knows everything. Newton said gravity is a force of attraction that acts between every two pieces of matter in the universe.
Wow, that's a big statement.
Okay, so let's take a look back at our comet. Comet, blah, 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 blah. So,
Churyumov Gerasimenko.
So, we have these two comets, and so we talked about how gravity is a force of attraction and acts between every two pieces of matter. So you've got this piece of matter, this chicken wing, and this leg right here, and it totally looks like food.
It does. It looks like food does.
Yeah. And what's happening is this is exerting a force on that, that's exerting a force on this, and it's bringing them together through the force of gravity.
Yeah. And Newton's third law.
Newton's third law, baby. So, what does this say about the force of gravity acting on you right now?
Whoa.
Well, that means that there must be a force of gravity between me and Mr. Boykin, me and that table, me and the sun, me and the moon, me and Jupiter. Doesn't matter where. Literally everything in the universe, there's some sort of force of gravity. There's some sort of interaction between the force of gravity between those two objects.
But I'm not feeling it. How can that be?
Why is that?
We'll have to find out.
Okay. Why doesn't the moon fall into the earth? Well, hold on here. So the question that I asked you guys before was, why doesn't the moon just go in a straight path? Right? The moon is just chilling, right? It wants to go.
Yep.
Right? That's the first law.
But
But what's pulling it in? The force of gravity.
gravity.
Yeah. Okay. So it doesn't go in a straight line. It curves. It does not go in a straight line because gravity is pulling it in. But then why doesn't it fall into the earth? What's going on here? Okay. Let's check it out. Oh, I forgot my mouse. All right. So this is the earth. This little red dot is my moon. Ready? Aim. Fire. Oh.
Well, that's Newton's cannon.
Yeah. Oh, yes. We call this Newton's cannon. You could look it up and find it yourself, ladies and gentlemen.
So how fast was that?
That first one was 31.
All right, let's
something.
do 41.
4,100 meters per second. Boom. Oh, lame. Let's put some pep in the step here. 53.
Whoa. So it's going faster, but it still, but it falls down.
Yeah. Let's go. Let's push it here. Let's go 64. And let's go ahead and try 68 maybe?
Oh, that goes really far if you think about how far it goes on Earth.
Yeah, a quarter of the earth. Okay. All right, let's go a little bit further. Let's go 71. And fire!
So it's So it's falling towards the Earth, but it was going, so if you go fast enough.
Yeah. Oh, okay. So it's clearly falling, right? Fall. It's falling. But what we changed out here was the speed.
Yeah.
So like you were saying, if it goes fast enough, it has enough speed to make it keep going.
Yeah, it's falling towards the Earth, and the path curves away at the same rate that the Earth is curving away. Fire that thing again. Let's hear it again.
Fire!
See it? Almost.
Gravity's pulling it in, but its speed is keeping it going.
What would happen if you made it go faster?
Ooh, let's try it. Should we max all the way out? Right there.
7,500.
And go. Oh no.
See, gravity's pulling it down. It wants to go in a straight line. But it...
Ow!
Cool.
All right. That's it for that, guys. So you should be able to answer this question. Why doesn't the moon fall into the Earth? And also, why doesn't it just go in a straight line?
Yep, those are important. That's what Newton was thinking about.
Yeah.
All right.
What determines how strong the force of gravity is? This is what Newton was trying to get at, what he was trying to answer. So, lucky for us, he has an answer. The magnitude of the force of gravity varies with the amount of mass involved. And we have this proportion, I'll talk about what that means in a second, to kind of break it down for us. So this thing right here is a proportion sign.
Yeah.
And it's like a little fishy or number 8 that's got the bottom cut off and top onto the side. And what this tells us is that there is a direct relationship between the force of gravity and the two masses that are involved.
More mass, more force.
More mass, more force.
Yep.
Okay. How about this part? And how far apart the object's centers of mass are. So here we've got the force of gravity is inversely proportional but it's on the bottom, to the distance, the square of the distance, arc radius. So what that means is the bigger the distance, the less the force.
Yep.
Whereas for the other one, the more mass, the more force.
Yep.
Okay. There is an attractive force between every particle in you and every particle in the Earth. Yeah. Whoa. What is this? What in tarnation?
That's you
That's me up there.
on the Earth.
He's gonna have to work right there. Okay. Ah, look at that. Okay. So this is. Oh, I just realized. Okay. So this is our Earth, and that's me up there. And what we want to look at is all the forces that are being exerted on me. And what's important to note is that the force up here is gonna be. Oh, how do I draw this? Should I draw on the board?
I'd put one over here.
No, let's put it over here. The force here, well, let's put a dot right here. Remember, any dot, I'm just gonna throw a couple dots on here, right? So the force of gravity between me and any particle, there's a force, right? The closer it is to me, the more force.
Yep.
Okay. I'm further away over here, it's gonna be a little smaller. Oh, this one's gonna be really small. Miniature. Okay, a little bit bigger right here because we're closer. A little less, right? You guys get the hang of this, right? Okay.
What would be the average of all that?
Okay, so if it's really strong up here and barely anything down here, if we were to cut this right in the middle, okay, we'd have some sort of average force,
Yeah.
right? Okay, so now we've cut it in half. Let's look on either side of me. So on this side, I've got some force pulling me this way, but
Yeah.
it's balanced out by the same force pulling me this way, right? So essentially, if I cut the Earth in half this way, it's almost like the average forces would make the center of mass right there in the middle.
It's as if all the mass were concentrated right there in that one spot.
Yeah. Okay, so out of those proportions, this is what we get.
Okay.
If there was a whole board all the way through the earth, what would happen if you fell into it?
God forbid.
Straight through hell. Say hi to Steve. Okay, so Exhibit A, our hole through the earth. Remember, every single particle that we have going on here is exerting a force on you. And so we have to think about what the net force on us is going to be. Okay, so you take a dive into the hole. Okay, so let's see where we are here. This is sort of the middle, just to have an idea. Okay, so first step into the hole, we start to fall. What's going on here? So we have,
Some of that mass is above you now.
yeah, so we've got a little bit of the mass of the earth here, but we have way more down here. So we have to take that into account when we're thinking about what the net force of gravity on us is going to be. So I'll use red to represent the down arrow. Okay, so actually, let me start here, right? Okay, most of the force here is going to be down
When you're on the surface.
on the surface. Actually, I'm going to go ahead and draw it over here so I have a little more space, right? Well, most it's going to be down when you're on the surface. Okay, now that I've stepped into the hole a little bit, again, most of it's going to be down, but it's going to be a little bit smaller, and I'm going to have a little bit of force up, because force is mass and acceleration, and I've got a little bit of mass up here, right?
Yep.
All right, so my force net
It's still going to be
equal
down.
Still down, right? Mainly down. Okay, this arrow a little bit bigger. There we go. They should be the same size. Yeah, they should cancel out. Okay, so next, I'm falling further. Okay, here I am now, having the time of my life. Falling straight to the center of the earth. Okay, wrong red, this one. Okay, and now my force down is going to be even less.
Why is that?
Well, because at this point now, I have less mass below me and more mass above me,
That's right.
right? And mass has an effect on the force. So, force net equals, in this case, still down, right? This one's still bigger than that one,
Not as big.
but not as big. Okay, all right, I'm gonna do one more here. Okay. Now, what do you guys think is gonna happen here?
There's more on top.
Smaller. Am I in the middle yet?
Not
more,
quite.
one more,
No.
Okay, so even smaller.
The
Okay.
arrow up's getting larger.
It is, oh, whoops, didn't make that one big enough here. Okay. Arrow's up a little larger, but this red one is still bigger. Arrow's not entirely drawn to scale. Okay. The force net, wrong color. For net for this one is almost, it's really small, right? Because this one almost cancels out that one entirely.
Yep.
Right? Okay. So now here I am hanging out in the center of the earth.
Are you not hanging out? You plummeted.
Okay. And at this point, what is going on with my forces? Well, I have equal amounts of mass below me, right?
Yep.
And above me. So at this point, oh my goodness, these guys cancel each other out. What is my net force going to be here?
0 if they cancel out.
0, right? What does that mean for acceleration?
Huh.
Okay, making my way through the earth. Okay, I'm going to skip down here a little bit because we kind of get the point, right? I'm going to draw 2 more of me. Okay, so at this point, I have more mass this way, huh?
Whoa. Yeah.
Okay, so that means that my force is going to be even smaller here, and it's actually going to be bigger over here. Net force is going to be that direction.
Up.
How
Whoa.
can that be? Well, this is hypothetical, right? Has anybody actually done this?
No.
Not yet. Okay, and when I'm right here, well, there's actually, I consider myself being on top of the other side of the world. I'm not going to have any force. There's no more mass below me. All the force is going to be that way.
Okay.
Okay, so the force net equals that way, right?
So if there was a hole bored all the way through the earth, what would happen if you fell into it?
Okay, well, let's talk about the acceleration, right? Like, what does this mean for acceleration? Okay, so acceleration, isn't the acceleration the same direction as the net force?
Yeah, always.
Okay, so that means that the acceleration is going to be this way. That makes sense. We're moving this way, right?
You're falling.
I'm falling. Acceleration equals, okay, so again, this way. It should be the same size, same direction. Okay, acceleration, oh, small. What does that mean? I'm not accelerating as much.
You're not pushing as hard down on the gas pedal.
Yeah, ooh, I like that. Okay, when the force net is 0, that means we have 0 acceleration. Okay, acceleration here. We're actually going the other direction. And then at this point, we're actually, acceleration is major time the other direction. Okay, so hypothetically, what this means is that as you would fall down, you would be accelerating less and less.
But you'd still be going faster, 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 faster.
But you're accelerating less and less and
Slower,
less.
slower, 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 slower.
And then what happens right here?
You better grab the edge.
Yeah.
You're going back in the hole.
Going back in the hole, right? So that is hypothetically what would happen. And the reason for this is because every single particle in the earth exerts a force on you and pulls you. And it's the net force that ultimately determines which way you are accelerating. Yeah.
Sweet.
Sweet. So ultimately, the takeaway, the direction of the net force is from the center of mass of one object to the center of mass of the other.
We saw that over here. The net force is always pointing toward the center of the earth.
Mm-hmm.
Sweet.
Center there. Okay, so moving right along here. Okay, So this is actually Newton's law of universal gravitation. But let's talk about what it is. It's a proportion that shows the relationships. It shows the relationship between the force of gravity and the masses of two masses and the square of their radius. Now, ultimately, this is not useful yet. So what Newton told us is that if we know the masses of our two objects and we know the distance between them, and we have the force of gravity, we can use this to calculate a constant proportionality that we can use to create an equation. So let's talk about how he did this. This dude named Cavendish.
This was like how long?
Like 1798. It's been a while.
Yeah, it was 100 years after Newton came up with his law of universal gravitation.
Yeah, I mean, imagine having to wait 100 years for the next big thing, right? And so what Cavendish did was he designed this experiment. I need my mouse. Always forgetting my mouse.
Actually, you can just click on it.
Oh, yeah, you're right. Okay. He developed this experiment in order to calculate that constant proportionality.
Yeah.
Of proportionality. And so I'm just gonna play it for the first time through. You guys can check it out.
Go.
Oh, I'm not over here. There we go.
Ooh. Oh.
What do you notice? What moves?
Ooh. Oh.
Okay.
Hit it again.
All right, here we go.
What do we got here?
Okay, so we want to be looking at the relationship between these two or these two. Okay, let's just focus on the left side for now. And so we have these two lead spheres, and we know their masses, right? And what happens as they get closer here? Ooh, what do you notice?
They move.
They move, right? Let's go ahead and play that one more time. And you'll see that they move on their own. And why is that? Well,
wait a minute. What's that thing in the middle? What's it hanging from?
so this is sort of like a spring. It's like when you take a piece of gum out of your mouth and you like pull it out, and it kind of looks like that. But it's made of glass, so it's kind of spring-like, which allows it to move. to twist. And what we see is, go ahead.
Well, it's like a spring, the more it twists, the more force is required to make it do that. And so the light shines off the mirror and is measured, the deflection on a screen.
And what is it measuring for us?
Okay. So right there, you've got a certain deflection. That's how far the spring moves at equilibrium.
Now, does that tell us the force?
Yep.
Okay, so we can calculate the force of gravity here.
Well, you measure the force of gravity.
So we can measure the force of gravity here, not calculate it, measure it. And we've got the masses, and we can measure the distance between both centers of mass, right?
Yep.
Doesn't that mean we can... Oh, sorry, I'm jumping the gun here. Doesn't that mean that we can figure out what the constant of proportionality is?
Yep.
Sweet, we have all those things that we need. Okay, so this is what Cavendish did. He developed this really sensitive scale that allowed us to measure the gravitational force between the two lead spheres, and voila. There's a constant relationship between the variables that we have here. Now, we just went over how Cavendish, he measured out the masses of the two lead spheres that he had. He measured out, he was able to measure the force of gravity, that laser-looking thing, and he could measure the radius between the two spheres. And it's important to realize that we still have relationships here, right? The bigger the mass is, the bigger the force is. The bigger the number on the bottom, the bigger the number on the top.
Yeah.
Whereas with our radius, the bigger number this is, the more distance we have, the bigger the number this is, the smaller the force of gravity is going to be. Okay, and ultimately the number that he calculated was this number here.
Wow! Look at all that.
Is it a big number or a small number? How do we know? Well, that negative 11 there tells us that it's a really, really, really small decimal. And what does that mean? Well, this is, the reason that this is a small number is because gravity's lame. Gravity is a weakling.
It is weak.
And so the force of gravity is really not that strong. So it only seems like it is because the Earth is big.
That's right.
Okay, so once he had that constant, what do you think the first thing that he did was?
I don't know.
Well, he said, hey, let's measure the mass of the Earth.
Wow!
Sweet! Okay, so in order to measure the mass of the Earth, he needed to find the radius first, right? Because that's part of our equation right here. Right? He needs the radius.
Oh, yeah.
Yeah, okay. So how can one find the radius? Well, this guy, Eratosthenes, he actually made measurements and calculated the circumference of the Earth within 16%. You got the circumference?
How did he do that?
You can find the radius. Good question. Next slide, please. Okay, so you know what? Actually, I drew this picture over here a little bit bigger. Step into my office. Okay, so how did he do this? What was going on? Well, so on one summer solstice, when the sun is like directly above, there was a pole shining into a well, and there was no shadow. Sun's right above, the sun's rays are coming in, and there's no shadow. And that was in Syene.
Syene,
right? Syene, right here. And so, like a year later, he's like, okay, let's see what happens if I'm in Alexandria over here. So again, pole, he looks down, but this time there is a shadow. Sun's coming in, and it creates an angle of 7.2 degrees on the ground.
What did he figure out when he saw that his post cast a shadow when it didn't cast a shadow in Syene?
Okay, the first thing he said was, hey, the Earth is round.
Cool.
Right? It's the only thing that makes sense. And so what he did from there was, we think about similar triangles. If this is 7.2, then this is also 7.2 degrees. Okay, what did he do next? Well, he said, okay, he walked from here to here. He measured from here to here.
He sent some guy.
He sent someone else to do his dirty work, right? And he measured that distance, that d. He also knows that 7.2, a circle is 360 degrees. 7.2, that's 1/50th right?
Oh.
So whatever distance this is, say it was 200 kilometers, I'm literally just making up a number. If I multiply that by 50, I'd have the whole circumference of the Earth, yeah?
And what can you do with that?
Well, with that, we can plug it into circumference C equals 2 pi r. Y'all all know about that. And in order to solve for radius, we can divide by 2 pi, and the story is...
Boom. The radius of
done.
the Earth.
Yeah. And so once you have the radius of the Earth, okay, then you can calculate the mass of the Earth. But this is the equation we have. So pause the video and solve this equation for the mass of the Earth.
Solve.
Okay, let's solve this bad boy. F of G equals G times, let's make that big. Mass of the Earth times mass just in general divided by radius of the Earth squared. Okay, so we're solving for this one right here. We're going to go ahead and multiply by this, multiply by this. We are going to divide. Do I need to explain it more in detail, or is it
Nah,
fine?
they can do this. They should have done this already.
Yeah. Okay, divide by this. And so we get radius of the Earth squared times the force of gravity divided by times mass equals the mass of the Earth. Let's plug and chug. I'm just gonna put it on this side, if that's okay. Let's see, plug in those numbers. So we want 6.38 times 10 to the 6 meters squared times the force of gravity, and we're going to use 9.80 newtons, divided by our G. What was our G again? Oh yeah, 6.67 times 10 to the negative 11th Newton meters squared divided
1 kilogram.
by kilograms. Okay, and then, yeah, did you show them that?
I did.
Yeah, okay, so we've got 1.00 kilograms. Cutting it close there. Okay, now to plug it into the calculator. All right. So I've got 6.38 times 10 to the 6th. And that whole
Don't
thing
forget
is
to square it.
Squared? Yeah, squared.
That's my mistake. I do that all the time.
Yeah. Oh, that's very true.
Did it yesterday.
I think about all our mistakes. Okay, divided by, and it times 9.80 divided by 6.67 times 10 to the negative 11th. Okay, no squared that time. Times 1.00 kilograms. Okay, ooh. And I get 5.981 times 10 to the 24th. Ladies and gentlemen, did we get the correct answer? Oh yeah, we did. Look
Sweet,
at that.
sweet.
Okay, I'll go ahead and write it up there for you guys. 5.98 times 10 to the 24th?
Yep.
What am I using? Oh, kilograms.
All right.
Oh, cancel all your units out, people. Okay. All right. And that's what we got here. Beautiful. Rock and roll, baby. Challenge question. In your notebooks, please write this down. And I want you to plug in the numbers and solve. Ignore this. Just focus on this. You don't even need to write that. But focus on this right here. The numbers you're going to use are these numbers.
For the mass of the Earth,
Mm-hmm.
for the radius of the Earth, and G is 6.67 times 10 to the negative 11.
Should we do this with them? Sure.
So pause the video, you do it,
Then check your work with me.
and then we'll do it. Okay.
All right, here we go. So we said F of G equals G times the mass of the Earth divided by R of the Earth squared?
Yeah.
Yeah? Okay. So our numbers, oh yeah, let's go on the other side.
I would just erase that force of gravity, that F sub
Oh
G.
yeah, let's get rid of it.
That's not what we're doing.
Oh yeah, only these things. Okay, so what does this equal? I'm just gonna write it over here.
I like that.
So our gravity number, oh, what was that
Okay,
number?
we're gonna have scientific notation, so you better make some room, girl.
I know. Okay, let's do this. Okay, my G is 6.67.
How you doing, my G? G.
Times 10 to the negative 11. Oh, here we go. Newton meters squared divided by kilograms squared. Okay, so that's this one times the mass of my Earth. That was that really big number. 5.98 times 10 to the 24th kilograms. And we're dividing this by the radius of our Earth. Our radius of our Earth was 6.38 times 10 to the 6 meters. Let's do it. Okay, here we go. 6.67 times 10 to the negative 11th times 5.98 times 10. Oh.
Don't forget to square the bottom.
Squared.
I made that mistake yesterday.
5.88 times 10 to the 24th. Okay, I'm going to divide that by 6.38 times 10 to the 6th squared. Boom. And I get, whoa.
That's 9.7. That's 9.8. Wait a minute, I know that number.
9.8. Should we do the units?
Okay.
Okay. So this is really meters squared. I'm just going to put the squared right there. So these cancel out, right?
Yeah.
I've got 1 kilogram here and 1 there.
What's a Newton?
Newton over kilogram. Newton force is Newton, right?
Yeah, it's mass times
So
acceleration.
Newton equals mass times acceleration, kilograms meters per second squared. So a Newton is kilograms meters per second squared
Over kilograms.
over kilograms.
So what cancels?
What oh, here we go. Cancel here. Cancel here.
Those are the units of. That's the acceleration due to gravity.
Acceleration due to gravity.
Damn.
Dang, all right. Okay, where's my mousey thingy? Okay, so they're the same thing, right? We took a look at this section right here, and so this is, we have this because of Newton's third law, Newton's law of gravitational,
Newton's law of universal gravitation.
because of, I'm tired, because of Newton's law of universal gravitation, and Cavendish helped us get that guy right there. And, you know, we started off with this,
Yeah.
right? The second law, F equals m times a, and so they're the same thing.
They're the same thing. Amazing.
That's good.
It is. It is.
Okay, so R is always the distance between the center of masses. We talked about that. Center of mass. And, oh, practice problem. Write this down in your notebooks, ladies and gentlemen. If you want to take a stab at it while I'm erasing, do it. Teacher strength. I wish I had like. Okay, what force of gravity acts between? So we're trying to find the force of gravity here. Acts between a bowling ball with a mass of 7.5 kilograms and a golf ball, a little golf ball, with a mass of. Sorry for the brief interruption, ladies and gentlemen. Miss Moore's alarm went off. Picking up right here, a golf ball with this mass, when their centers are, radius are, 0.25 meters apart. Okay. F of G equals G M1 M2 divided by the radius squared. What was the G again?
6.67 times 10 to the negative 11.
Small number.
Newton meters squared over kilograms.
Okay.
That took me about 5 years to memorize.
Yeah. I mean, that's why they have the AP sheet. The AP, the cheat sheet, right?
Yeah.
Okay. So let's go ahead and plug this in. So 6.67 times 10 to the 11th, negative 11th, Newton meters squared over kilograms squared times mass 1. Doesn't matter which one, we're going to go with this one first. Kilograms times 0.032 kilograms. And we divide the whole thing by the square. Where's my radius? 0.25 meters squared. All right. See if you can get it, ladies and gentlemen. All right. 6.67 times 10 to the negative 11th times 7.5 times, I'm eternally grateful for non-scientific notation numbers, 0.032, divide that by 0.25 squared.
Big number, little number.
I got a little number.
What'd you get?
I got 2.56 times 10 to the negative 10th.
And what are the units of force?
Newtons.
There you go.
Forgot my number already. 2.56 times 10 to the negative 11th newtons.
Boom, boom, boom.
Boom. A small number because the force of gravity is weak.
Weak.
Weak sauce.
All right.
All right. You are going to answer these next few questions on Canvas, but I'm giving you a little sneak peek. First question. Why doesn't the moon fall into the earth?
Ah!
Whoa. And then, second one. A 100 kilogram satellite is orbiting that many meters above Earth's surface.
Surface.
The surface. We'll come back to this. What is the force of gravity acting on the satellite? Okay, back up here. So this does not include the radius of the Earth.
Oh, because the force of gravity is between the centers of mass of the two objects.
So this is not the distance you want to use. That's your hint.
So
Okay, I want to factor in what the radius of the Earth is
I like that.
to this.
They can figure it out. They'd
Yeah.
be smart.
Yeah, you got it. Next question, third question. What would be the force of gravity acting on the Earth due to the satellite? This has to do with the question that we just asked.
Yeah.
So, what would be the force of gravity acting on the Earth due to the satellite? Okay.
And this is Newton's third law of motion, isn't it?
Yeah, this is a little bit of a hint here.
Oh.
Third law. When two objects interact, one exerts a force on the other. There is a simultaneous force exerted back, equal in magnitude and opposite in direction. Go get them, ladies.